Hello. Today I'll be presenting the paper Attending Knowledge Facts with BERT-like models in question answering, disappointing results, and some explanations. This presentation will be about two experiments that we made while working on question answering with BERT and the surprising results that we got. First of all, why do we want to work on question answering? It is one of the core tasks in natural language processing, and it is one of the most challenging. Current state-of-the-art models do not achieve human performances on a lot of benchmarks. And this is necessary to achieve true AI interactions with humans. We need to be able to build models that understand questions and are able to generate answers that are both accurate and realistic. In addition, we have access to a lot of benchmarks. A lot of them have been introduced in the past years, and they provide us with the necessary annotated data to train deep learning models. Talking about question answering as just one task is a bit misleading. It is a collection of tasks. One such task is extractive question answering, in which the questions are joined with a reference text, and the competing models are required to select a specific span of text that contains the answer. One example of extractive question answering dataset is Squad. Squad has been introduced in 2016 and is very popular. You can see on the left here an example of question in Squad, with the question and the corresponding span answer. One thing to know about Squad is that current state-of-the-art models do achieve human performances. You can see on the right here the current top of the leaderboard for Squad. And thus, there is not much space for improvements. Another type of question answering is multiple choice question answering. This will be the type of question answering that will be the main focus of our work. In this type of question answering, questions are adjoined with multiple answer choices, and competing models need to select the right one. An example of this kind of question answering dataset is OpenBookQA. OpenBookQA provides 4 possible answer choices per question and no reference text. The competing models thus need to rely on general world knowledge to answer. This dataset training set is composed of about a few thousand questions, and instead of a reference text, OpenBookQA provides a list of science and common knowledge facts, which models may use to extract world information. These facts are provided in the form of little sentences, and the main difference between science facts and common knowledge facts is that science facts have been used while creating the dataset, and thus there exists a link between each question and a particular science fact that gives information for this question. In the normal settings, models are not supposed to use this link, but we will use it in our experiments later on. On this dataset, human performances are not achieved yet, and thus there is a lot of space for improvement. You can see the current top of the leaderboard on the right here. Another dataset that we used is ARC. ARC is really similar to OpenBookQA in the sense that it is composed of multiple choice questions with 4 answer choices and no reference text. It also provides with a list of facts, and it is divided into 2 parts, easy and challenge. The challenge part being composed of the questions that were unanswered or answered incorrectly by a bunch of baselines. And again, on ARC, you can see that the results, the accuracy results, are not yet high enough or can be improved. As you can see, both OpenBookQA and ARC provide us with additional facts that models may use to extract knowledge about the world. But most current state-of-the-art models do not use these additional knowledge, and instead they rely on pre-learned knowledge. They extract their knowledge from training sets and from eventually pre-training when they use pre-trained models. This has two major drawbacks. First, it creates a low generalization capacity, since in order to be able to answer correctly at test time, you need to see that particular piece of information during training. And secondly, something that is really related to the first point is that it requires a lot of data, since you need to be able to cover the entirety of the application domain in order to be able to answer to the majority of questions at test time. Instead, we would like to teach our model how to extract relevant information directly from the database and use this in order to answer the question. This can possibly allow for an easier generalization because we'll be able to add domain-specific information into the database at test time. And it can also require less annotated data because it will be easier to transfer knowledge from one dataset to another by, again, adding extra information into the database. And this will be the main motivation of the following work. Before we go to the experiments, I need to talk about BERT. BERT is a pre-trained model. It is based on the transformer architecture and trained on book corpus and Wikipedia. It provides a contextual embedding of the words inside a sentence, and thus can also provide an embedding of a sentence. BERT showed really impressive results on a large number of tasks in NLP, including question answering, and currently most state-of-the-art models are on a lot of benchmarks are pre-trained models. BERT is provided in two versions, base and large, and for the rest of this presentation we will be using the base version of BERT, mostly because of computation power limitations. We also used sentence BERT. Sentence BERT is a fine-tuning of BERT on SNLI dataset, and it has been trained. SNLI dataset is a dataset in which you have couples of sentences, each labeled with entailment, contradiction, or neutral, and they trained SBERT with a Siamese architecture and a triplet loss in order to bring closer together the sentences, the embeddings of sentences that were supposed to be entailments, and further apart sentences that were supposed to be contradictions. And they claim that the representation provided by SBERT capture more semantic than the representations of BERT. The first model that we will use is the vanilla setup for question answering with BERT. In this setup, the questions are concatenated to every answer choice, and each of the resulting sequences that we obtain is embedding using BERT. The embeddings are then sent through a linear layer, and what we obtain at the end is a single Scala score for each answer choice. And we will compare these scores together with the softmax, and the model is trained using a cross-entropy loss by comparing this distribution that we obtain with the softmax and the gold answer. This setup is supposed to get around 55% with a BERT base and 60% with a BERT large model. So it's quite far from state of the art. But as I said before, we obtain similar results with more performant models, and thus the results that we will show later on need to be compared with each other and not always with the state of the art. In this first experiment, we wanted to know what parts of the questions BERT was using when answering a question. To do so, we trained our models without any additional knowledge facts and with part of the questions removed. For example, we tried experiments where we kept only the last 4 tokens, or experiment when we removed the first 4 tokens, or even experiments where we keep only the first tokens. And all these experiments gave around the same accuracy scores. You can see on the table, in the table here, the accuracy for a model trained with the full question and a model trained only with the last 4 tokens of the question. And what we observed is that when removing tokens, all the models were around the same, like around 52% accuracy. And it doesn't decrease much in comparison to the full question model. And so we decided to go even further and remove the question completely. So the model was fed with only the answer choices and no question, and was asked to find the right answer. And we should expect in such a setting to obtain 25% accuracy overall. However, as you can see here on this third line, the scores, the accuracy of our model is still high. It's still higher than 51% accuracy without even the questions. This means that our model found a way to distinguish between right and wrong answers only using the characteristics of the answers themselves. And this shows that there exists a big bias in our dataset. We ran similar experiments on ARC and we found similar results. The accuracy of our models never dropped below 36% accuracy on easy and challenge, even without the questions. So this means that this kind of biases can be found in multiple question answering datasets. In order to find out what kind of biases could cause the results that we showed before, we computed some statistics on the dataset, and we found that right answers are in general longer than the wrong answers, and that right answers generally contains at least a word that is less frequent than the words in wrong answers. We tried two models. One model that always selects the longest sentence, and one model that always selects the answer choice with the less frequent word. And we obtain respectively 33% and 37% accuracy, which is, well, lower than the 51% obtained by BERT, but significantly higher than the 25% that we should expect from such simple models. And this shows that those two characteristics are biases that could influence the training of BERT. Here is an example taken from OpenBookQA dataset. So the question is, what impacts an object's ability to reflect light? And we have 4 possible answer choices: color palette, weight, height, and smell. This question is very interesting because it features both of the biases that we presented above. It's obviously selected manually, but when you know what to look for, these kinds of examples are not very rare in the dataset. And here you can see clearly that the right answer, color palette, is the longest of the 4, and also contains the word palette that is significantly less frequent than the 3 others. Let's move now to the second experiment. The few models from the state of the art that use the facts provided along OpenBookQA do so by selecting a subset of facts and then concatenating them to the question. They thus obtain a very large question with extra context. One of the problems with this is that it creates really long sentences, and this requires a really large GPU memory. And the second thing is, since BERT is a black box, you cannot use very complicated structures on top of BERT. What we wanted to do was to use an attention mechanism that would, on one side, get the embedding of the question plus different answers, on the other side get the embeddings of the facts that we selected, and then use an attention mechanism to select the relevant facts for each question, and then obtain scores the answers according to those facts. We will compare two models. The first one is the vanilla setup for BERT, in which the knowledge facts are concatenated to the questions. And the other one is an attention setup in which the facts are selected using an attention mechanism. We will also compare two sets of facts. The first one in which we only take the gold fact. This is a particular science fact that is relevant to the question, since it's been used when annotating the question, when creating the questions. And we will also compare it to another setup in which we hide this fact among other facts. The other facts would be a list of 9 facts that we automatically selected using word overlap. We conducted these experiments on OpenBookQA. Here are the results. When using model CAT, the results of BERT and SBERT are similar, which means that we observe a significant increase in accuracy when adding the gold fact concatenated to the question. When using an attention model with only one fact, the gold fact, we should expect a similar improvement if the embeddings capture enough semantic. However, with BERT, that's not the case. It turns out that BERT showed no improvements over the baseline with an attention model with a gold fact provided. However, SBERT was able to obtain a slight improvement of its accuracy. For SBERT and SBERT only, it turns out that keeping only the last 4 tokens of the questions actually improves the results. So we use the attention, when using the attention model with SBERT and with this only the last 4 tokens of the question, we obtain 61% with only the gold fact and nearly 57% with gold fact given among other facts. All these experiments seem to show that the embeddings of BERT do not capture enough semantic to be able to use it in an attention mechanism. However, SBERT showed really interesting and encouraging results, since you can see that if the right facts are provided, it is able to improve. In conclusion, we have to put in perspective the results of machine learning models on OpenBookQA. Since a model without the question is able to obtain at least half the question right, results of 70 to 80% seem a bit less impressive. Also, it becomes increasingly important to understand how deep models are making their decisions. And finally, it gives us an opportunity to work on bias prediction, since we have here a perfect example of a biased dataset, and it's a really good opportunity to work on models that are able to learn relevant features without taking bias into account. So that's all. Thank you for your attention, and don't hesitate to write comments or questions. I will be happy to answer them. Have a good day.